Welcome to this last discussion session for the conference. And first Mithat will present for 10 minutes. Then Misha,
Okay.
and we'll have a discussion.
Okay. Thank you very much. So obviously I am not Arkady, but Arkady asked me to talk instead of him. So I am happy to do so. I will be talking about very briefly about adiabatic continuity on R3 cross S1 and some open questions. So just last week, we heard some very nice talks about large N loop equations by Martin and Valya, and also an interesting talk by Davide on the use of one-form symmetries in Yang-Mills theory. So we all witnessed, and history proves that loop equations are very difficult to solve, and it requires this heroic work of but they are actually very handy to use if you are willing to compare theories. For example, they are used very extensively in the context of large and orbifold and orientfold equivalence, for example, between unequal ones for Yang-Mills and QCD with two-index representation fermion symmetric or anti-symmetric, as well as historically it is used in the context of Eguchi-Kawai reduction, which is large and volume independence. And interestingly, the key player in the Eguchi-Kawai reduction is the one-form symmetry and the realization of the one-form symmetry. So let me describe what what large and volume independence is, and from there I will go to adiabatic continuity. So the theorem is as follows. You can start with a lattice field theory in infinite volume, and you can reduce the field theory to arbitrary number of sites. And you can even reduce it to a matrix model, one side. And it turns out that there is no volume dependence in the leading behavior of topologically trivial single trace observables, for example, Wilson loops, as well as their connected correlators. If there is some, for example, time direction, there is no volume dependence, provided there is no phase transition as the volume of the space is shrunk. So there is, more technically, there is no spontaneous breaking of the center symmetry. And the proof of this statement goes through large N loop equations in the lattice theory. And the most instrumental part in this theorem of Eguchi-Kawai is that the word provided. So the one-form symmetry is supposed to be not broken. But if you do this in ordinary Yang-Mills theory, with the usual compactification on T4, actually, center symmetry, as you shrink down, breaks down spontaneously. If you do it, for example, on R3 cross S1, this is the usual thermal phase transition. And there is, let us now stay on R3 cross S1 instead of shrinking all the space. It turns out that if you add a double trace operator, which stabilizes the center symmetry at small l here, you can actually make the theory satisfy large N volume independence. You can shrink the S1 site to arbitrarily small values, and the dynamics is independent of the S1 size. There is a sector of the theory which is independent of the S1 size. It includes topological susceptibility, mass gap, etc., etc. The idea of adiabatic continuity is the baby version of the volume independence. Volume independence is a statement that really says that the observables are independent of L, compactification reduced. Adiabatic continuity says that as a function of L, there is no phase transition. For example, with this double trace deformation, what happens in Yang-Mills theory, as you shrink it, without the deformation, there is a deconfinement phase transition. But turning on this deformation, you can find a small circle regime, which is adiabatically connected to R4. The prime example of this is QCD adjoint in 4 dimensions. If you compactify on R3 cross S1 and employ periodic boundary condition on the circle, it doesn't break center symmetry. And on small circle, you can prove confinement analytically. So this is the goal. This is the generic picture. There is a phase transition, and this is what we want, adiabatic continuity. And this had been a topic of extensive research in the last 15 years. And I just want to tell you the results. And recall that many people in the past used to believe that confinement, mass gap generation, discrete or continuous chiral symmetry breaking, or topological susceptibilities are necessarily strong coupling phenomenon in 4D QCD and QCD-like theories. The new thing we learned is that all of these phenomena can actually be realized at arbitrarily weak coupling. And this weak coupling regime is adiabatically connected to strong coupling. And this brings, in my opinion, many interesting questions. To give the flavor, I just want to mention pure Yang-Mills. Pure Yang-Mills are Abelianized. There are n sorts of monopole instantons. They have topological charge 1 over n, action 1 over n. They proliferate, and they generate a mass gap. Mass gap is given by this formula. And it involves this lambda square, and small parameter is lambda ln. And it involves this multi-branch function, and you have to choose the branch with max. And this is the mass gap of the theory on small circle, semi-classical regime. However, I want to mention, this is the semi-classical regime. I want to mention a very interesting lattice result, a fairly recent one by Massimo Delia and his friends. They measured topological susceptibility, and Alexandru is also around, so also mass gap in Yang-Mills theory on R4. This is, of course, very well known. Also in deformed Yang-Mills theory on R3 process 1, it's small circle. Here is the surprise. If you do not put deformation, topological susceptibility dropped like a rock. You know, it is very well known. If you insert this double trace deformation, this is a fairly small circle. Temperature-wise, it corresponds to 500 MeV. Topological susceptibility at very small circle is identical to the one on R4. Similarly, they calculated mass gap, and these are lattice data points with this deformation parameter. And it's again fairly small circle, and mass gap on arbitrarily small S1 agrees with the mass gap on R4. So my question one is following. Why, even for SU3 theory, is topological susceptibility and mass gap agrees between the theory on small S1 times R3 and R4? So this is the first question. You know, in semi-classical analysis, we derive a mass gap, but it's not identical to what you obtain at large, you know, at the lattice simulations. Lattice simulation is really capturing something about strong coupling still. But my surprise is that why does the weak coupling capture so much about the strong coupling? Here is a, again, thought-provoking question. Is it possible that semi-classical bases that emerge at weak coupling on R3 cross S1 may actually be a complete basis in the sense of saddle point analysis? You know, it may be capable of describing multi-branched observables, which are where each branch is 2 pi m periodic, but observable is 2 pi periodic. Well, another perspective is you can, even on R4, you can at arbitrarily large form manifold, you can couple Yang-Mills to TQFT. And we all know that for PSUN theories, topological charge is quantized in units of 1 over n. So the interesting question is, what is the non-perturbative expansion parameter? Is it S instanton or S instanton divided by n? And I believe that the answer is S instanton divided by n, even in the SUN theory. And I will finalize here. So in a fairly recent work with Yuya Tanizaki, what we showed is that we compactified many interesting QCD-like theories, including QCD and Yang-Mills themselves, by using 2 Hooft flux on R2 times T2. T2 is small, and we inserted some units of 2 Hooft flux. And for Yang-Mills theory, the theory realizes semi-classical confinement due to center vortices. This is the first semi-classical realization of the center vortex scenario. So what we learned is something that is, in my opinion, exciting, because we learned that Yang-Mills theory admits at least 2 different semi-classical regimes thermodynamic semi-classical regime in which confinement mechanism seems to be different. One of them is monopole instanton, the other is center vortex. So both of these configurations have topological charge 1 over n. And the open question is, how do we reconcile these two types of semi-classical confinement with each other? And what can it tell us about the, about the analysis of the theories on R4? I think I should probably stop here. So I completed my 10 minutes. So looking forward to the discussion session.
Okay, thank you. Now let's Misha.
Stop share.
Thank you very much. So I will start, I will suggest a discussion on a different topic, which was only marginally mentioned only marginally in this program and in this conference, but tomorrow I will have a detailed talk on that. So I will start with this picture of a long thin string. Well, in the critical case, it's an infinitely thin string, which was discussed very nicely by Dubovsky and Gorbenko, as you see here, the names of the authors. So they make an attempt to build not 10-dimensional critical string, but to descend down to our 4-dimensional non-critical string by using the strategy. Start from 10 dimensions, deform it as seems meaningful or sensible, and then explore. In particular, they use 4-dimensional effective field theory, expanding derivatives in Nambu-Gato action, add some additional terms which they deem necessary, use additionally bootstrap data, approximate integrability, and so on. And then they simulate this scattering of the massless excitations of the string, which exists due to the massless excitations in 4 dimensions due to the translational moduli, the motion in the plane perpendicular to the string. You see here this long string, x1 and x2 are two axes perpendicular to the string. And they produce some results which later can be interpreted as hadronic scattering or hadron spectrum in 4 dimensions. Now I will present to you a totally different, I would say opposite approach, because in this approach we start, this approach was developed by Jung and myself in the last decade, basically, or a little more. And here we start from 4-dimensional Young-Mills theory. We don't know anything about 10 dimensions. And we see what can be done inside or in the framework of 4-dimensional Young-Mills theory, whether we can ascend in a sense to 10 dimensions and what we could do en route. The simplest example was this of this type. This is referred as non-abelian string, and I want to emphasize that non-abelian doesn't mean a string in non-abelian theory, which can still be abelian. On the other hand, you can have non-abelian string given in supersymmetric QED. Non-abelian string that there exists on the world sheet of the string some extra moduli or some collective coordinates which belong to some space with non-abelian, which the target space of this moduli is endowed with non-abelian symmetry. So the simplest example was of this type was simplest non-abelian string was found by Tong and Hanani. They went from a string side and but Jung and Dai and some other collaborators, Jung's collaborators, we approach this issue from pure field theoretical side, and we advanced, I would say, more than from the string side. So we have n equal to, supersymmetry is n equal to, extended supersymmetry, 8 supercharges in the bulk. And we will get eventually an example of a confining string which has n equal 2 supersymmetry on its whole sheet. You remember Zohar mentioned the other day that there are no such examples, or they rarely appear. This is the only known to me example when we have n equal 2 supersymmetry, both in the bulk and on the string whole sheet, and the string confines. So what this theory is? It is Young-Mills theory with n colors and n flavors. The number of flavors has to be equal with the number of colors. The symmetry of the theory is not SUN, but UN. Why is that? Because we want to add the Fayet-Leopoulos term, which can be done only in the case you have U1 gauge subgroup. So this is crucial, because without the Fayet-Leopoulos term, you cannot maintain n equal to supersymmetry in the bulk and the string whole sheet, which is strong enough to allow for very careful predictions. So in this case, we have two flavors and two colors, we get the simplest CP1 sigma model on the string whole sheet. That is to say, two modular fields or three unit vectors, n with three in internal space. They have three coordinates subject to constraint n squared equal to 1. So this is classically, this theory breaks SU2 symmetry, and it has two gapless excitations, two goldstones. Quantum mechanically, of course, as usual happens, the infrared interactions restores completely SU2 symmetry, and this happens due to the fact that if you include quantum mechanical effects, all these unit vectors situated on the string became start oscillate like crazy, and their orientation is totally smeared over the spherical S2. Now, an interesting story, an interesting aspect, which I want to mention right away. If you draw the running of the coupling constant, you will observe that the four-dimensional coupling constant runs at one loop according to the standard law. Then it's frozen at the point, I forgot to mention that two flavors completely Higgs this model at a certain large scale, and at this scale four-dimensional coupling freezes, but the coupling on the string whole sheet, CP1 coupling, continues to run exactly as this coupling in 4 dimensions. If you draw this curve 4D to D, you will not notice any transition. It's completely smooth. In particular, if you manage to do your gauge theory conformal, keeping N2 supersymmetry in the bulk, the corresponding two-dimensional theory is superconformal too. Now, what happens? This is the simplest example, and we consider a large amount of various examples of this type. And then we discovered that the sigma model on the string whole sheet there are very many, a huge class of them. Especially interesting becomes the situation if you break n equal 2 supersymmetry down to n equal 1 by a small perturbation. Then you will see that the theory on the string whole sheet becomes heterotic. The number of left movers and right movers is not equal. And this is there are very interesting versions of this model with lots of unusual properties, which I think have never been discussed in the past. Okay, now let's move on further. Now let's consider a variation of this strategy and introduce SU2, still U2 symmetry, but instead of two quarks, we consider four quarks and squarks, 4 meta hypers. Okay, the bulk theory is almost conformal because you remember this: the beta function vanishes if an f is equal twice the number of colors. I say almost, because the Phi-Heliopoulos parameter, which does not run, nothing runs in this theory. There is no scale lambda. But the Phi-Heliopoulos parameter is dimensionful, and therefore vacuum expectation values still develop. The theory is fully Higgs. You can consider it both at weak and strong coupling. You see, the theory n equal 2 has 8 supercharges. The string it supports it 1/2 BPS. So BPS string contains 4 supercharges. It still have non-abelian vortices, supports non-abelian vortices, but in this case, for flavors, they becomes not like similar to Abrikosov, they are semi-local string. Correspondingly, the bulk theory, the theory on the whole sheet, as I mentioned, it has to be conformal, and it is a very unusual theory also. I didn't draw it. Okay, let me tell it in words. The theory now, instead of 2 moduli of the type n modular, we have altogether 6 moduli, some of them of the orientational type, like n fields on the previous transparency, and some of them are of the dilation type. Their oscillation described dilation. The theory on the world sheet becomes a superconformal theory, which is called weighted CPN-1, CP1 2,2, CP2,2 model. 2 n fields with the electric charge +1 and 2 ρ fields with the electric charge -1. So the manifold on the target space is no longer S2 is fair. It's a conical manifold of the Calabi-Yau type. If you look what happens on the this string made of flesh of blood, the target space is Calabi-Yau. At a certain point in the space of the coupling constant, this becomes a singular, it's always non-compact, it becomes a singular Calabi-Yau. At this point, we can consider this string and analyze the spectrum of this emergent string. You see, it's remarkable because we started from 4D Young-Mills and we developed a 10-dimensional strings, 4 normal coordinate x and 6 moduli, all of them massless moduli because it's conformal field theory. But unlike conventional case, they live not on compact Calabi-Yau, but on non-compact Calabi-Yau. This decimates the spectrum of excitation of the closed string, which we explored in a couple of papers. The last one was, I believe, pretty recently. And what is given here are the spectrum of 2 spin of 2 massless states. They have 4-dimensional spin equal to 0. This theory doesn't have massless tensor particle, massless graviton, which is very important. This is inclusively due to the property of the target space. It is non-compact, and many states which exist in a regular critical theory disappear because the 6-dimensional wave function becomes non-normalizable. So the graviton disappears. There is no spin 2 massless states. However, there are spin 2 massive states. You see them here. And the number of other spin 2 massive states, they are labeled, but what we call baryon charge is not a real baryon charge, it's some U1 symmetry, color flavor locked symmetry, which is a remnant of our bulk theory. So I want to, I'm just a little bit over time, but I want to stop at this point, and those who are interested will have the opportunity to listen it in more detail tomorrow. Thank you. Now I think it's time to open general discussions.
Thank you. So somebody wants to start? Shota?
Hi, I wanted to ask a question to Mithat. So it's about this deformity unmills, like about volume independence. How much was computed in the a matrix model, the reduced matrix model? Like what observables people computed and how people compare them with the actual unmills?
So this is a topic of quite, extended period of time, which had been revived more recently in the last 10 years or so. But most serious things are devoted, for example, to the calculation of string tensions, expectation value of large Wilson loops and string tensions. And those things are nicely calculated. As far as I know, for various representations, various free energies are computed. For example, if you shrink 3 direction, stabilize center, and in the 4th direction, let's say there is nothing to stabilize the center, then you can see confinement, deconfinement transition. It matches to pure Yang-Niels theory very nicely. And you can do appropriate continuum scaling, etc. Those kind of thermodynamic behaviors also match. The work on spectrum is lesser. So I mentioned not fully reduced matrix model, but on R3 cross S1, there was this paper by Massimo Delia and his collaborators, and they did study on a lattice system emulating R3 times small s1, and they put a double trace deformation on the small s1. And in that case, they calculated the mass gap, and maybe one of the authors may be here, but maybe it's too late in Cyprus if he's not here. So, and they obtained something very close to the result at 0 temperature for the mass gap. But there is work in the context of QCD adjoint, which works, deform Yang-Niels on R3 cross S1, which works. And there's also work in the context of twisted Teguchi-Kawai, which is a very interesting model, incorporating 2-Hooft flux, and many works in there as well.
Thank you.
Sure.
Please wave if you have something to say on this topic, but if not, then Arkady, I think, was the next.
No, I was going to ask, after Sylvia talk, it's a bit more technical, but still wonder about, this anti-periodic boundary condition. But if you believe that it is like a space dimension, right, then you can put any boundary condition. So I wonder about possibility to study this periodic boundary condition.
Yeah, I mean, I think the problem with periodic boundary conditions is that for massless fermions, there's some zero modes.
Yeah.
But if those can be taken into account properly, I think that shouldn't be a problem.
I see. Yeah. So there is no, principal problem on the way, right? So you can try to do it, yeah? Because it was related to this discussion of central symmetry in particular, right? So that's why I wonder.
I think it's more challenging for sure.
Yeah.
I mean, I don't know to what extent. Probably Igor knows more about this. Yeah.
I wouldn't say that it's a problem. It's a feature of the fermion zero modes. I mean, they're required to capture the right physics in the infrared. It's not a bug. It's a feature.
Yeah.
But one needs to learn how to deal with it properly.
Right. Yeah.
I know that for small volume, small length, the analytical treating of this problem, anti-periodic boundary conditions are much more convenient, that I know.
No, but of course they are more convenient because less to count modes, right? But if you're going for, say, this center symmetry, for example, then it becomes another problem, right?
Okay, I just don't know that they're more convenient, and probably in the calculations of Klebanov, they're also more convenient.
While we're on this Can one study something like, can one study scalars? Because it would look a lot like dimensional reduction of 3D on mills, but are scalars much harder in this procedure?
Yeah, I think one has to worry about the renormalization of the mass. But yeah, I think it should be possible to study them too. Yeah.
Yeah, we had a paper back in '93 on the scalars. Yeah, and indeed, that's not a completely finite theory. You have to renormalize the scalar mass squared appropriately. But yeah, it makes it more like gluon. And as far as zero modes, yeah, it's a perennial topic of discussion among light cone experts. I remember I went in '93 to a LightCon workshop and all the talk was about zero modes. And I think all the talk is still about zero modes. Yeah, it would be great to settle, at least for the fermions, it seems definitely easier because there's still a finite space, right? Yeah. But still it's a large space. So yeah, I feel like the anti-periodic choice cuts everything off nicely, and if you're after a limited set of things, say the spectrum of bound states in the trivial vacuum, that should be fine, that should be good enough. And but yeah, the more ambitious things, yeah, I'm hoping to just study this theory on the spatial circle. I mean that, and we have started doing some of that.
We studied the QCD adjoint with or without four Fermi deformations on R times S1. It is quite interesting actually. So if you take just periodic boundary conditions, then of course on R times S1, the center is unbroken and the fermions along the Cartan subalgebra remains gapless. And so you can reduce it to quantum mechanics, and you can show that there is a very large dimensional Hilbert space constructed out of these zero modes. It's like 2 to the n-1 dimensional, or 2 to 2n-1, very large. But when you turn on these four Fermi deformations in the QCD adjoint, then these degeneracy do get lifted, and you know, quite a bit. And this is also probably related to content of the Zohar's paper concerning non-invertible symmetries, etc. That these operators break the non-invertible symmetries.
Yeah. I think even without these operators, there were studies by Shifman, TS, and Lamb.
Yes.
Back
very nice. Yeah.
In the small circle limit. Yeah, I think the n vacuum are exactly degenerate, and then it's in the small circle limit, but it's not totally clear what happens with these additional vacuum. I don't think all 2 to the n-1 are degenerate, but maybe they show up something. But yeah, in that formalism, it should be no problem to turn on the four fermion operators and check what.
Right.
Yeah, in this light cone approach, they seem very hard because they have the structure of psi left, psi right, psi right. So you can't just trivially sort of integrate out psi left in favor of psi right. It's just somehow much more interacting problem.
Right.
Actually, I had the question for you. Could you remind us, so your double trace deformation involves trace of the Wilson loop on the circle?
Of course, yeah.
If you could just remind what it is.
Okay, let me do share screen. And so it is, you can actually construct it in multiple ways, but the operator I wrote it here is like this. So it is square of the Polyakov loop going around the S1 direction. But this operator actually can be induced if you have, for example, massive adjoint fermions in the game and integrate them out, at sufficiently small circle, they generate this operator with positive coefficients. Actually, I think there is some people do not like it because it is, you know, the circle, it is, of course, if the circle size is large, this is non-local, but the circle size is fortunately very small. And from the perspective of the 3D effective theory, it's fine. The surprising thing to my mind at the time was that this is an operator which is order n square, and yet it doesn't affect observables like mass gap, topological susceptibility, string tensions, despite being order n square. And that's one of the very subtle points. I think there is one more way to do this. You can take R2 times a very asymmetric T2 and take the T2 direction, one of the directions of T2 very large, and insert a two flux. And S1 direction is small, and that will force the holonomies in the S1 direction to be roots of unity. So that will stabilize center symmetry. That is almost R3 cross S1, and it doesn't use any double trace deformation or anything like that. Just inserts two flux, and it achieves the same results.
Can I ask a related question, which is, if I'm a continuum observer at very short distances compared to the box, what kind of perturbations to the normal Yang-Mills action do I see?
From this operator?
Yeah.
I don't think you see anything interesting.
So you don't even see anything power suppressed?
No.
You have to be global at the box size to see anything at all.
If you think of it, Lance, if you think of it as a very heavy adjoint, you know, fermion induced potential,
yeah,
you should not see any impact on.
Well, there would be power suppressed stuff. There would be an F cubed, a G cubed operator instead of G mu nu squared. In that case,
maybe I am not sure. Yeah, but that may be possible. Some mass suppressed operator of
something that's power suppressed.
Yeah.
But that would then be power suppressed with the size of the box somehow?
Three dimensions of the box is infinite already. So only one is, okay. You are asking the impact on the short distance physics or long?
Yeah, and whether it breaks any local Lorentz invariance. It's supposed to preserve gauge invariance.
Yeah, it
preserves Lorentz invariance locally.
If you think of it as a very heavy adjoint fermion, of course, it doesn't harm Lorentz invariance.
Yeah. No, but it's not, Mithat, it's not going to work like that. If you just integrate out a heavy fermion, of course, it's going to induce a million other things. This is not Lorentz preserving.
Since you are on compact space, it's not Lorentz preserving, but there will be an emergent Lorentz symmetry here, because when you have this, the Kaluza-Klein modes are not quantized in units of 2 pi over L. They are quantized in units of 2 pi over Ln. Even if your L is fixed, as you take n to infinity, it will form a continuum. This is very similar to Gross-Kitazawa derivation of the beta function of pure Yang-Mills theory on R4 by using just matrix model at a point.
But if you say there's a continuum of states, then it seems like that's going to, and they're associated with one dimension and not the other 3 dimensions. It sounds like it's going to break Lorentz.
No, 3 dimension is already infinite. What I'm saying is that the modes in the compact direction are not quantized, perturbatively speaking, are not quantized in the usual terms of Kaluza-Klein modes as 2 pi divided by L. Rather, they are quantized in units of 2 pi over Ln. With L
so they're
fixed,
very light.
They are very light.
Okay.
With L fixed, if you
but they're associated with one direction of the 4 Euclidean directions.
Yes.
So then the Euclidean symmetry, the O4 is broken probably. Or...
because of the compactification, yes. But
Okay.
in the n goes to infinity limit, I think for some observables, it doesn't matter.
Okay. Thanks.
Sure.
Sorry to interrupt.
No worries.
I think Ofer has a question.
Yeah, so I also have a question for Mithat. I mean, so you presented two cases where you conjecture that there's no phase transition. I mean, on a circle and on a torus at finite n when you put the theory there. So what is the evidence for this so far? I mean, you presented one graph for this one case of the susceptibility, which looks smooth, but what other evidence is there that there's no phase transition in the middle?
In the middle. So people checked it on the lattice. At least there is simulation results by Massimo Delia, and they see that with the appropriate deformation, there is no phase transition in the middle. But there could have been. Your question is right, and there are circumstances in which there are. In fact, in the setup, you can also work, turn on some one-form symmetries, etc. And with this, you can show that there is a, this is something shown by Zohar and his friends. On R4, they show this mixed anomaly between one-form symmetry and CP, for example, for the case of Yang-Mills. And this thing in this background survives on R3 cross S1, this anomaly. So there is a similar anomaly polynomial with one dimension reduced, but there is a mixed anomaly between theta angle periodicity and one-form symmetry. So even if there is a phase transition, so it should be something respecting to, anomalies.
And then for the torus case, do you know if anybody tried to simulate it? I mean, with a set of Flux?
Torus case, we just wrote it. Actually,
yeah.
Torus case is very interesting to my mind. We posted the paper just last week or more than a week ago. It was very surprising to us. But we had our very concrete, interesting cases that we did not see that, there is no intermediate phase, but we could see that, for example, one very interesting case is following. If you take QCD with arbitrary number of flavors, okay, and you can turn on a U1 baryon flux, and you can show that in the small circle regime, in this background, Dirac operator has certain number of fermionic zero modes, actually n of them, and f of them, if you have n f flavors. And one of the flavors is eaten by the center vortex operator. But now this thing is supposed to be continuously connected to chiral Lagrangian, right? Because on very large T4 or R4, I have a chiral Lagrangian, but with some U1 baryon background turned on. But if you examine what the current is, current turns out to be Vesumino-Witten term. So if you add to this chiral Lagrangian, if you were to reduce it naively to 2 dimensions, you would get a nonlinear sigma model, a principal chiral model, and it would be gapped. But when you have the Vesumino-Witten term, level 1, it reduces to a CFT, and if you look to its central chart, it is n-1. The number of degrees of freedom, etc., matches. So this was one of our best evidence for the adiabatic continuity in arbitrary flavor of QCD. There is again similar story with super Yang-Mills or pure Yang-Mills in all the other cases we have examined. There we have many tests actually in the paper, but I am sure that much more can be done both numerically and as well as analytically.
But on one of the previous slides, I think you were suggesting that maybe somehow saddle points remain the same as one goes from weak to strong coupling. But isn't this example in some sense contradict this? Because here you have two different semi-classical descriptions with different set of saddle points.
That's a very nice question, actually, Sergey. The shocking thing is following, okay? And maybe I am also asking to you, all of you. In the case of monopole instantons, okay, these are saddles. Monopole instantons are saddles, and their topological charge is 1 over n, and their action is 8 pi squared divided by g square n. we know these solutions. We can solve them, okay? There is no two-Hooft flux here in this story. This comes out of the dynamics automatically, as it is. Here, in the case of R2 times T2, you can insert one two-Hooft flux on one of these T2s. You can insert another two-Hooft flux on the R2 compactifying to T2. There is again a quantization of the topological charge, but now that quantization is really dictated by bundle topology, right? Because you are in the PSUN and topological charge is quantized in units of 1/n. There are very important open questions. For example, in the case of these theories in two flux background, the semi-classical configurations are not known concretely. There is only one known solution. It is due to 2-Hooft, and it is on a T4, and it's a constant solution. It's very boring solution. On the T4, both electric and chromoelectric and chromomagnetic parts are constant. And on R times T3, as well as R2 times T2, the evidence for this center vortex type solution, etc., a BPS solution of this kind, which saturate the BPS bond, is completely numerical. Neither on R times T3 nor R2 times T2, people do not know analytic configurations, analytic solutions, which satisfy the BPS bond. This is a open and, to my opinion, very important question. And I suspect that I asked this question many people in this audience from time to time. But the interesting thing is, in both cases, you have topological charge 1/n objects. And in one case, you cannot show, in the other case, numerical evidence by Gonzalez Arroyo, Margarita Perez, and their collaborators show that, you know, they are really BPS. They calculate electric action, magnetic action, etc. It is with great precision that they match to each other. So in this sense, action of these two different configurations, monopole instanton versus center vortices, are same. Maybe one may, I don't know. Yeah, this is all I know right now. Both of them generates the same theta angle dependence, θ/n. And this θ/n is the instrumental quantity when we start to look to, you know, to theta dependence of the observables in vacuum. You know, we must obtain some multi-branch function, n-branch function. Each branch must be 2 pi n periodic, yet the observable itself must be 2 pi periodic. And as far as I can see, both of these bases satisfy exactly this. They seem to be, you know, for such function, I can write a Fourier basis, very simple analysis. And these semi-classical objects match to that result. This is the surprising thing to me.
When you say BPS, do you mean what? You mean self-dual field strengths, or what exactly?
Self-duality equation. Its solution for the fractional topological charge configurations are not known.
Well, globally, the charge is integer. You mean like fractionalized kind of solutions?
Yeah.
But isn't it in the moduli space of ADHM?
That's a very good point. I think so, but at least I personally think so. But to see them, I think we need a better parametrization of the moduli space. I think that the traditional parametrization that we use is not very handy for that. In 2 dimensions, there is a parametrization by Fatev, Schwartz, and Frolov, as well as Lucher and Berg. They have a simultaneous paper. They study CPn-1 model. They do not usually CPn-1, it should have 2n bosonic moduli. And usually it is parameterized in the reviews in a particular way, but they parameterize it in terms of complex variable and complex variables. And I think that is the clever parameterization. And at least in my opinion, that is the thing that we should do on R4.
Other questions? Yeah. I had a question to Gabriel actually about this. Like I'm trying to think about connection of these line defects to flux tubes. So let's say take this gauge theory and perturb it such it becomes confining in the IR. Then I can study confining flux tubes and I can take kind of UV limit of the confining flux tubes. So does like this information which we are getting on conformal defects, does it tell us something about behavior of confining flux tubes, or it's really different regime and there is no connection?
That's a good question. And somehow it's crucial for our arguments that that the line sources a profile which spreads far away in the bulk. So in this sense, something is opposite to confinement. So in this sense, some negative about the connection, but there might be, you know, like as you said, I understand what you're suggesting. Suggesting the UV, you have more something like conformal, and the R becomes a flux tubes, and then we just have to find something in between. And we didn't think about that. And not sort of some extra comments.
I don't have anything intelligent to say, but you know that for the real life flux tube, you have a conformal regime, and when they become long, you have a confining regime. So there should be some function that interpolates, right?
Yeah, so that the question is,
for instance, you know, kind of operator content on this line defect. Is it related in any way to the spectrum of excitations which one finds on the flux tubes, or kind of questions like that?
Yeah, it's like asking, given the spectrum of operators in a CFT, you deform it by mass, what is the connection to the spectrum of masses? And so this is like what these people that do Hamiltonian truncation try to do, basically, right? That's the central idea, but I don't know of analytic results.
yeah, so. But okay, so I think the concrete question would be if one can develop an approach to explicitly perturb the UV and try to, for like, I think there's an Hamiltonian truncation through the way. And I mean, it sounds an incredibly hard question, but maybe these Hamiltonian truncation methods have some translation to this or something. But I don't believe you can do it analytically with our technology for sure.
Yeah. Adi, you have a question?
No, it's to Misha, because I'm trying to talk about this string, you know, they invented. But my recollection is that it is still kind of a string of magnetic field, if I remember correctly, right?
Yeah, that's right. In certain cases, it is possible to do the dualization and pass to change everything electric into everything magnetic and vice versa. But most of the examples we consider, it's the magnetic strings. Of course, when at strong coupling, like for instance in CP1 model at strong coupling, you cannot really say because the magnetic flux starts oscillating like crazy and SU2 restores, but still basically it's a magnetic string, so it confines monopoles, not quarks.
Yeah, but when you say the dualization, it would be interesting to see example of such type of dualization, right? Because I mean, it's not clear whether it even exists in this case, right?
In some awkward cases, you won't be happy with it, but okay. Most often, you know, I wanted to say that these particular strings are not specific to n equal 2 supersymmetry. They can be very well described in n equal 1 supersymmetry. As I said, in most cases, these theories end up with the chiral heterotic model on the string world sheet. So you have to deal, in order to understand the spectrum and so on, you have to deal with this heterotic model. There are two types of them. The minimal one, which exists only for CP1, but we came across a non-minimal one, which exists for any CPN and can be solved in the large N in the strong coupling regime. Also, even in QCD, high density QCD, you know, these strings exist in high density QCD. That's one of the example where they kind of are dual-line. Non-supersymmetric, you have high density QCD, it's a very particular example, maybe cannot be even experimentally studied, but at least in this example, if you assume that all three quarks, UDS, have the same small masses, then you come across a non-supersymmetric non-abelian string, which is interesting by itself. The assumption is not very realistic because this quark is much heavier, and this is crucial in this model that there's quark. But because, you know, in general, when NF is equal to NC, this is a special point. You know, we know many examples of that in the other problems, and here in dense QCD, that's also the case. If you have three light quarks approximately of the same mass, it's the same. It works good. It's stable then. Also, in many solid state problems, we have a similar situation. For instance, in the B phase of helium-3 superconductivity, you can see that such a non-abelian string is important instead of the Abrikosov string. And now we're considering, you see, there's such an effect which was suggested to us by Cvelik in two so-called two-component superconductors, when you have two other parameters which are distinct but are constrained, have a certain constraint. You know, this is an example when non-abelian string emerges in the.
Yeah, muted, Misha. You mute yourself.
This is an interesting example because that's an example where it may emerge a non-abelian type string also of a different type. Its target space is S3, so it's kind of a principal chiral model. It emerges in the theory where underlying theory is just electrodynamics. And then you can play, but this is, we just started doing it under the suggestion of Cvelik. That's all I can say.
Okay, thank you.
Can I ask Misha one question?
Yes.
I remember that there was some dispute about whether it's really true that the string supports this non-compact Calabi-Yau sigma model.
Yes.
Some issue with the modes being non-normalizable in the bulk. What is the status of that?
No, this is a standard. You see, in the bulk, it's a standard n equal 2 theory. Itself, you know, it's even can be, you can solve it. Well, solve it, a la Seiberg and Witten probably. You have to take into account the Fayet-Leopoulos term. There is no problem. Well, moreover, if you have four flavors, it's in the bulk, it's almost conformal. Why I say almost? Because there is a psi parameter, Fayet-Leopoulos term, which has masses, and then it constrains, it forces some vacuum expectation value of matter hypers to develop, to be non-zero. So it's kind of spontaneously broken, if you wish, spontaneously broken conformal theory in 4 dimensions. At the quantum level, nothing runs. You see, the energy trace of the energy momentum tensor is presumably, at least anomalous part of the trace of the energy momentum tensor is 0. And when you go onto string world sheet, it's just a conformal theory, but okay, it has some moduli the number of moduli in the target space for many states is non-normalizable. But this happens, right? In other examples.
Right. There were some articles saying that the string would become infinitely fat because this radial mode is non-normalizable.
You see, when I say, for instance, take spin 0 states, which we discovered at the first stage using supergravity. You see, when I say it's normalizable, it should be understood that it's only marginally normalizable. It's the norm of the measure in the transverse dimension is a logarithmic integral. So usually the states, you may say that strictly speaking, the normalizing integral requires some further regularization in the infrared. But it's also a common case that logarithmically localized states, you know, they are assumed to be, or they are treated as localized. Most of the states have seriously divergent norms, you know, like for instance, spin 2 state has a seriously tensor states has seriously, so it all goes to infinity in the 6 extra dimensions.
Mish, in a simple example was with this color orientation modes in normal instance, where it also was problem of normalizability in regular gauge.
Yes.
You remember, it's not just example of what we are saying.
Yes, yes. No, but this is it for zero energy state. You see, you don't feel any mass parameters for those. So logarithmic integral, normalizing integral is very natural. So, but you know what, for massive state, which we have discovered, we have to learn little string. We used little string theory, and this was very hard for me to learn, you know, using Kutasov papers and reviews, but it works, you know. You definitely define a number of massive states which are attached to. This is the closed string, you know. You form a closed string, and then you see. If you don't go, you see, let's say you don't want to go the road to go all the way down to the critical string. Let's say you consider the original SU2 model. Then, of course, the theory on the string wall sheet is non-conformal. It has the scale parameter lambda, the same scale parameter as the theory in the bulk. So, strictly speaking, this moduli becomes quasi-moduli because CP1 model develops in the infrared a mass gap. But you can still treat them, you know, and then another step which we have done, which was very important, in CP1 model, you have two distinct vacua, okay? And so these two distinct vacua being supersymmetric as degenerate. From the bulk standpoint, it means that you have two distinct strings with the same, exactly the same tension, which is degenerate, degeneracy is guaranteed by supersym. If you have two distinct strings, then you have a intermediate domain where one interpolates into the other. So you get a kink. In the quasi-classical approximation, you get a kink, but then you have to quantize it. And the fact you see upon quantization, or even quasi-classically, we did it long ago, noted it with Smilga, that in fact in SU2 theory, there are two such kinks. And kinks, because the SU2 symmetry on the wall sheet is completely restored, the kinks form representations of SU2. In particular, the simplest kinks are doublets in SU2. So from two doublets on SU2, you can build a singlet, SU2 singlet and SU2 triplet, enjoy it. So you will have I don't cannot find, but I will describe it later. You will have each kink. You see, each kink is attached to non-abelian string, which carries 1/2 of the magnetic charge of the 12th pollock of monopole. So they take together, they take the both charge. So in order to make a confined meson, which is localized, you have a monopole, anti-monopole, arrange them in the adjoint representation of the global SU2 flavor symmetry, okay? Then they cannot annihilate, and they're connected by 2 strings. You know, one monopole emanates 2 strings which are absorbed by the anti-monopole. So this is a bound state. Of course, it's not a bound before dualization. It's not a bound state of quarks, but this is an example of how this non-abelian string can bind monopoles.
What is the coupling constant of these strings?
The coupling constant, well, it depends on the coupling constant of the bulk theory. Of course, if you want to get something like a critical string, which I described, which is a string in 10 dimensions, you have in the bulk theory to go to strong coupling. And here you can do that only thanks to very strong holomorphic relations which exist in N=2 supersymmetry, basically extending the lines of the Seiberg-Witten solution. There is one critical point of cell. You see this CP2,2 has apparently has a dual point. You know, at a special value of a coupling constant, you can exchange rho fields with n fields and nothing changes. So you have to go to this dual point where the coupling constant divided, the bulk coupling constant divided by 4 pi is equal to exactly unity. And at this point, the Calabi-Yau develops a conic singularity, and you start quantizing it, and you get these 2 massless baryonic, well, quote unquote, baryonic states, which I mentioned. So if you want to go, why you need to go to strong coupling? Because the strings you study, which are hairs or descendants of the critical string, they have to be very thin, right? So the string which I mentioned originally, it has the thickness typical to lambdas, to the scale lambda of the Young-Mills theory. It's not infinitely thin. But there is a one point in this particular example, one value of the coupling constant, where the thickness of the string becomes very small. So it can mimic the critical string. But you have many other examples where the string, of course, the Woold's sheet theories on such strings are not UV complete. You have to learn how to. But it's a physical, you know, it cannot be unphysical because you have a string made of field well-defined for renormalizable 4-dimensional field theory. If you go to very short distances to very high momenta, you just probe your theory at very short distances, and then it's the same as the 4-dimensional field theory. If you scatter very energetic, you know, fields, then there for very energetic fields whose energy is much larger than lambda QCD, there is no difference between the localized string, 2D string and 4D bulk. So,
but that's exactly why I'm asking, because as I was trying to say early in the program, I think interesting thing about confining strings is that there is a decoupling limit. One can go to planar limit. In that limit, the strings become well-defined objects up to 2-dimensional up to arbitrary high energies. So I'm trying to see whether there is anything like that for this.
Excuse me, somebody disturbed me via phone call. Can you please repeat, and I will switch off my phone. least make it. Okay, could you please repeat, Sergey, what did you say so I can answer you?
Well, I think what's interesting about confining strings is that there is a limit where one can, namely thought limit, where one can really turn them into UV complete two-dimensional systems. There is a decoupling limit where one can decouple all bulk excitations. Yeah. And I'm trying to see whether there is anything like that for strings you are talking about.
You see, in the simplest case, you build a string as a soliton, supersymmetric or not supersymmetric out of field theory. It has its thickness. The minimal thickness you can achieve if you build it out of some field theory is lambda scale parameter of this theory. This is a typical case. And also it happens at strong coupling, because at weak coupling, its theory is its thickness is determined by the Faye-Eleopoulos parameter, which you have to have much larger than lambda QCD. If you
so if one goes to energies above that tension of that string, energies above inverse thickness, is there any sense in which this theory, the string still exists as a two-dimensional subsector, or it just
only in this particular example which I mentioned, where the string builds itself through the moduli space becomes two-dimensional string line on a Calabi-Yau type singular manifold, non-compact. That's in this example, you can, after that, you can forget about the bulk theory at all and deal with the string theory per se. It's totally UV complete.
Can we imagine that we are living in this world, that there is somewhere the string and our world, I mean, our four-dimensional world, is a part of your construction?
It's a very interesting question. You see, with the proliferation of the number of examples, there may be, for instance, the Witten's cosmic strings can be, the class of these cosmic strings can be essentially enlarged using these ideas with non-abelian strings. This is also an exotic example because Witten strings, cosmic strings, have never been found, and there are speculations that they are inflated away. So this is also exotic. But in condensed matter theory, we're seeing more and more examples where it can describe important physical phenomena.
No,
I think maybe because we have a talk tomorrow by Misha, so we'll have.
I will present tomorrow a 1 hour talk, and I will try to, at least the first half of the talk will be totally understandable to the beginners, absolutely explicitly in simple terms with very few equations, and the remainder of the talk will be I will just formulate the results and give a flavor of how they are obtained, and then you can ask questions, whatever you want. I will be happy to answer.
Okay, so probably at this point, then we should wrap up discussion and really thank the organizers, Misha.
Including yourself?
Huh?
Including yourself?
I'm not the organizer of the conference, so. No, I'm thanking really Misha, Igor, Pedro, and Monica. And Marek for organizing this conference under very, very challenging conditions. I think we all have fun. And well, I'll see you, many of you now in person.
Okay. Okay. Thank you. Bye.
Yeah, I want to thank all the speakers and discussants. It's been great. Yeah.
Thank you, everyone.
Thank you.